In this video, we're going to look at a second deep connection between accumulation points and convergent sequences. The authors of our text state this particular connection as theorem 61. If we have a sequence of pKs that converges to the point x, and pk is not equal to pk plus 1 for all k inside the natural numbers, then it turns out that x is an accumulation point for the set of terms of the sequence. Now, in order to prove this theorem, we actually have to pick this apart to figure out what it is saying and why each piece of the hypothesis is important, as well as figuring out what the goal is to show the conclusion is true. So I'm going to actually start out with talking about some scratch work. Stuff that I need to do in order to be able to figure out how to start in on this proof. And the first part of the scratch work is in dealing with what it means when we have that particular hypothesis, because that's a peculiar looking hypothesis. So what I want to be thinking about is, why must pk not be equal to pk plus 1? And what I really mean by this is, what does this hypothesis say? And the importance of this hypothesis is that it's going to prevent us from having a sequence with what I'm going to call a constant tail. So suppose for just a minute that we have a sequence of pKs that looks like, oh, I don't care what P1 is, I don't care what P2 is, I don't care what P3 is, but eventually I get down to Pn, and then the rest of the sequence is just C, 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 forever and ever and ever. In other words, if k is bigger than or equal to n plus 1, then pk is equal to that constant. Now, what I want to note about this particular sequence is the following. Clearly, this sequence is going to converge to the constant that is the constant tail. So let me actually kind of point that out. This stuff here says that we have a constant tail. We have some beginning terms over here, but at some point, the only term that we have is the thing that we're converging to, written over and over and over and over and over. And since we get to a point where we're just hitting the same point over and over and over, convergence to that point is no problem. But what I also want to note is that the set of pKs consists of P1, P2, down to Pn and C, and this is a finite set. And we know that finite sets have no accumulation points. So I want to recall that. A finite set has no accumulation points. So this hypothesis that I'm boxing in red here means that we are not going to be on a sequence with a constant tail that is a finite sequence that has no accumulation points. And I want to state that very, very clearly. If it turns out that pk can be equal to pk plus 1, then we might have a constant tail, and sequences with constant tails converge, but do not have any accumulation points because they're finite sets. So the theorem would not be true if we dropped that particular hypothesis. So dropping pk is never equal to pk plus 1 would mean the theorem is no longer a theorem. The conditional promise could be broken. So this is a critically important hypothesis. Well, let's continue looking at our scratch work. So what's the next point that I want to be thinking about? Well, all right, I now know that I have a sequence that has a non-constant tail. So with a non-constant tail. And I also know that this sequence converges to the point x. And the definition of converges to the point x means that for every open interval S that contains x, there has to be a capital N inside the natural numbers such that if little n is bigger than or equal to capital N, then I know that Pn belongs to set X. All right, and one thing that I want to make a note of is that open balls are open intervals. So I'm going to kind of write this down. If delta is some kind of thing that's bigger than 0, then the ball centered at x of radius delta is an open interval that contains x. So there is going to be a capital N based on the size of that delta ball. So I'm going to call it N sub delta, such that if little n is bigger than or equal to capital N sub delta, then I know that Pn is actually inside this delta ball. And that's another important thing that I know. Now, the third thing that I'm going to be talking about in terms of scratch work is putting together what I'm wanting. I want to show that X is an accumulation point for this infinite series, this infinite sequence. And this infinite sequence does not have a constant tail. So what does that mean? That means I need to show that if I take some open interval that contains X, I can find some pk inside my sequence such that, first of all, pk belongs to that delta ball, and second of all, that pk is not going to be equal to x. And that's going to be critically important in thinking about this. So I want to think about what this stuff actually means. This stuff here, what that really means is I need to show that given any delta bigger than 0, I can find a pk on my sequence that lives inside the punctured delta ball and of radius delta. That's going to be the ultimate goal in our proof. We'll look at the formal proof of this theorem in the next video.